a special physics lecture to be delivered by Professor M. Lakshmanan. So may I now request our Vice Chancellor Maharaj to say a few words.
It's a matter of great joy that Professor M. Lakshmanan is here with us. So I feel nostalgic about having been with him, I think about nearly 45 years ago. Nearly 45 years ago, we were together as research scholars in the Department of Theoretical Physics. In the University of Madras in those days, there were 3 physics departments: Department of Theoretical Physics, Department of Nuclear Physics, and the Department of Biophysics. And Department of Biophysics was headed by the legendary G.N. Ramachandran, who later on went to Indian Institute of Science, Bangalore. And Department of Theoretical Physics was very interesting because very few universities have departments devoted completely to theoretical physics only. The origin of this, as you know, goes back to Bhavan and his group. TAFR is also part of that. One of the students of Baba Alladi Ramakrishnan in those days, his students spread out and started these departments. So Professor P.M. Matthews was one of them. He was a student of Alladi Ramakrishnan. Alladi Ramakrishnan was the founder and director of Institute of Mathematical Sciences, now the IMSC in Madras Taramani. And P.M. Matthews is the person who was the head of the department for a very long time. And both of us were students of P.M. Matthews. He was, of course, just a couple of years senior to me. When I just joined the department, and P.M. Matthews was a person who, he was also quite youngish at that time, I think about in his 40s. And the kind of anger which he used to show, most of the students would have run away if your guides and supervisors were that tough. It was very tough, and then simply he'll throw a paper at you. Some preprinters come from ICTP, Indian the International Center for Theoretical Physics. He'll simply say, report on this next week. What is it about? We had no idea what it was about. So we used to run around from pillar to post and the library to library, ask this person, and then when P.M. Matthews and all the faculty members were around, it used to be a nightmare for us. So this kind, of course, we learned so much because of this nightmarish experience. And I remember that I was struggling in the beginning as I thought I can't bear this anymore. I had to run away from here. I'm so grateful to Professor Lakshmanan who is here. Not that I'm not Professor Lakshmanan, not even Dr. Lakshmanan. So he was mentoring me with great care. The first paper which we wrote, I think in the unharmonic oscillator, we wrote a paper together, which was published in those days, the Nuovo Sumento. I don't know whether it exists even now, from Italy. So that was our paper, and he was a person who mentored me with so much of care and love, for which I even now remain so grateful. So we have been trying to get him for a long time, and we are so happy he's here. He came for the Indian Institute of Science Education and Research in Kolkata for a conference. He is now one of the very reputed scientists in the same field with our Dr. Shami Gupta is working, nonlinear dynamics and statistical physics and so on. So I think you have a separate department of nonlinear dynamics, which he heads now under the School of Physics. He moved on to Bharathidasan University, one of the very reputed universities in India, State University, which recently got A+ grade, which is not easy for a state-sponsored university to get that kind of a grade with very little funds and the kind of politicalization of in the appointment of faculties and so on. They don't enjoy that kind of freedom which we do. But in spite of that, Lakshmanan, we have seen him as such a hard-working person, calm, quiet. He used to speak very less, extremely focused in research, and of course he got the reward for it. And a man of outstanding conceptual clarity as far as research and physics is concerned. So it was a joy to work with him. And then I moved on to a slightly different field, but he continued in that field, nonlinear dynamics. And he himself discovered certain problems. He was also in ICTP for some time, even as a research scholar. I think for about 6 months he was there, and he picked up several problems. And he was also working on some neurophysiological problems. Huh? The synaptic basis of memory. I remember the paper which you wrote when I was a student. So we're extremely happy to welcome him today, Professor M. Lakshmanan, and he will be talking about some aspects of nonlinear physics and evolving science. And please feel free to ask questions and interact with him freely. He'll be leaving tomorrow morning, so make the best of use of his presence here. So I welcome Professor Lakshmanan, and I request Shamik to say a few words about his work after I finish. In the meantime, we have two pleasant jobs to do. One is a few books which are going to present to Professor Lakshmanan and his wife. This has Swami Vivekananda's books, and one is about 100 years of work in service which Ramakrishna Mission has been doing, a saga of service for more than 100 years. And Dr. Swami Gupta, as you know, has written a book very recently, and it will be formally inaugurated today by Professor Lakshmanan, and he wants to hand over a copy to the library, or the monk in charge of the library is present. And we also have Swami Dhanagamyananda, Swati Prabhu Maharaj, who is the internal quality assurance cell coordinator. So I welcome our Pitar Pavlik. You call it, you pronounce it almost, yeah. So please excuse our pronunciation. Of course, you can't also pronounce my name, a complicated name which I have. So all of you know, perhaps, I think by this time you have made friendship with him. He is with us, I think, for a couple of months now. He is so happy. He likes Indian food, and he likes Vedanta, he likes yoga, and he likes Indian classical music. And I'm happy to welcome him also, and welcome all of you. So this Shamik's book, as well as presentation of memento to Professor Lakshmanan, and then we go. Thank you. Synchronization, the Springer, Samit Gupta, and Alessandro Campa and Stefano Rufa. So what is the price of the book?
It can be downloaded.
This book is priceless.
Priceless.
You can give a copy to this book is for the library. So you can briefly talk about his work.
Hello. Okay, so it's a great pleasure and honor for me to introduce today's speaker, a very distinguished speaker. He's known worldwide for his contributions in the field of nonlinear dynamics and chaos. So he has worked on many different topics in nonlinear dynamics and chaos, including solitons, integrable systems, magnetic and optical solitons, classical chaos, quantum chaos, spatio-temporal patterns, synchronization, secure communications, and the list is really endless. So he has over the years written about 350 research articles in international reputed journals, and he has 8 books to his credit. 8. I just wrote one, and I think I'm not going to write another for the next. Okay. He has. So it's quite interesting that he has been able to achieve so much despite his teaching duties, or because of his teaching duties, that he could do so much in research. He has about 40 years of teaching and research experience at the Bharathidasan University, and he has mentored more than 32 students for their PhD degrees. And as is often the case in science, that it takes time, but people are there, people are watching you, so recognitions did pour in. From quite early on, I mean, he has been, he was well recognized in the field. So he has received some of the highest scientific awards in India, including the Shanti Swarup Bhatnagar Prize in Physical Sciences in 1989, the UGC Hari Om Trust Meghnad Shah Award in Theoretical Sciences in 1990, the R.D. Birla Prize of the Indian Physics Association, more recently the Shastra G.N. Ramachandran Award that he got this year, 2019. And he has also been a recipient of some of the prestigious fellowships like the DAE Raja Ramanna Fellowship, the DST Ramanna Fellowship, the INSA Senior Scientist Award, the NASA, the National Academy of Sciences of India Platinum Jubilee Senior Scientist Fellowship, and also some of the distinguished international fellowships, for example, the Alexander von Humboldt Foundation Fellowship, the Swedish Guest Research Fellowship, the Japan Society of Promotion of Science Fellowship, the ICTP Senior Associateship, and he has been also on the editorial board of some of the major international journals in the field of nonlinear dynamics and chaos, and he has served on several important national committees, including the selection committee for the Bhatnagar Award, the NET exam committee, the national level entrance exam committee, the National Board for Higher Mathematics, NBHM, the selection committee for the Swarna Jayanti Award, DST expert panel for first track scheme for young scientists in the area of physical and mathematical sciences. And he has also served on the FIST, this DST FIST committee. And thanks to him and his colleagues that our department got to the tune of 96 lakhs, with which we could develop the laboratories that we have here in our department. So I think the story would not be complete, if I don't tell you something about my personal experiences. I mean, I would like that the story be complete with those personal memories. So I think I met Professor Lakshmanan for the first time in 2004, when I was a beginning graduate student, and I had come with my PhD advisor, Professor Mustansir Barma, to attend first ever national workshop on nonlinear dynamics, which was held at IIT Kharagpur. And obviously Professor Lakshmanan was there, and he had to be there because before him, nonlinear dynamics, studies of nonlinear dynamics did not exist in India. Our life was too nonlinear that we never bothered to study nonlinear dynamics. So he was really the first one to initiate studies in nonlinear dynamics in our country. So that was for the first time that I met him. And then, after that I didn't have a chance to meet him. Of course, I was aware of his work and his books and so on. But when I was in Europe for my PhD, for my postdocs, then once in a while I would meet a European, and he would say, you are from India, I've been to India. So where did you go to? Calcutta, Chennai, Bangalore, Delhi, Mumbai? No, I've been to, and then with a lot of difficulty, he would say Tiruchirapalli. So, Tiruchirapalli, whom did you? And then I would know the answer that would be coming. Professor Lakshmanan. So, that was the status that he enjoys. And I think he is a prime example of a theorem that I always believed, and now I have a clear demonstration of that theorem that says that intelligence cannot be a function of space. Your intelligence could be a function of time. It may so happen that with age your intelligence may go down, or it may go up, but it certainly cannot be a function of space. That it cannot be that you are in a small place and then you become absolutely stupid or unintelligent, and then suddenly you get to a happening place. That's the term that they use nowadays, a happening place. What a happening, something has to happen all the time. I don't know who does that, but okay. So he's a prime example of someone who started really, from scratch, really. I mean, I gather by talking to his students. I had the pleasure of visiting him in February, and I had also the pleasure of meeting and discussing and chatting with his PhD students. And I gathered that when he joined Bharathidasan University, the university was merely, it was not even a university. It was just an kind of extension activity of the Madras University. And his students showed me a tent-like thing, like a garage or something, where he started all his activities. And from there, he grew to such a stature that everybody, he's a name to reckon with in the field of nonlinear dynamics. Wherever you go, if you are working in nonlinear dynamics, definitely people would have known him and would have had a chance to interact with him. That's really something to it's a lesson to learn. And I would end by saying one more thing that really served as a big inspiration to me, that I realized by talking to his students that over the years he has mentored a lot of PhD students, like 32 PhD students. Most of them came from very insolvent background. Okay, I think that's a great job. That it's quite easy to help someone who is already well established and has a stable situation financially and otherwise, but it's not easy to pull someone out of where he or she is at that moment because of circumstances, sad circumstances and so on. And I gathered that I've really been impressed by the fact that in the whole of Tamil Nadu, wherever you go, any small city you go, there would be a college where there would be at least one student of Professor Lakshmanan teaching and doing research. And over the years, he has taken it really like an evangelical task to go around, visit colleges and give lectures and workshops to motivate young minds to pursue research in physics and in nonlinear dynamics. I think just for this count he really needs a loud round of applause from all of us. I think it's a great job. Okay, so with further ado, I would like to request Professor Lakshmanan to kindly. Do you have mobile or something? No key or anything? It starts to make sound.
Thank you very much, Shami. First of all, I would like to thank the VC Maharaj for his very kind words and recalling our past joint work at University of Madras. Before I go along, I would like to first congratulate the VC Maharaj, all the colleagues in this university and as well as the students for achieving or for getting this A++ in the NAC peer committee evaluation, because that is one of the highest achievements, particularly a young university like Vivekananda University, which was started only a few years ago, reaching such top level is really a great example for newer institutions to follow. So I wish the university as well as the Department of Physics and the School of Mathematical Sciences, etc., to achieve greater heights in the years to come by. I wish them all the best. We had a wonderful time, but 45 years ago, I vividly recall, in spite of the demand made by Professor Matthews, we could survive and we could do some useful work. So it was a very pleasant experience to work with your VC Maharaj in those days. And I also find him to deviate in a different path, and he has come up extremely well. And it's a great thing to meet him again after 45 years. Shamik Gupta, a young physicist who have joined this department, whom I had personal experience of enjoying his science a couple of months back at Trichy. I really enjoyed his visit, his talks and so on. And well, he had made certain statements which I really thank very much for the kind words he had expressed. But I want to emphasize again, it is the place where or the circumstances at which you are forced to work doesn't matter. Wherever you are, as long as you are motivated, I feel that you can achieve great things. I think in this university itself, Swami Ramakrishna Paramahamsa, Swami Vivekananda, they've all achieved great things coming from whatever the circumstances they have come up. But I think they have become great and they have got so many followers. I think in the same way, particularly for young people, irrespective of the institute or the place, etc., where you work, you can come up to the top level and to the service of the nation if you are suitably motivated. So with these few general words, I would like to turn to my the topic of my lecture this afternoon, Nonlinear Physics and Evolving Science. So I do see a lot of students among this audience. So what I intend to speak about this afternoon is to give a kind of overview of the subject as I have learnt over the past 4 decades or so, and the kind of contributions our own group could make in the last 4 decades and so on. Yeah. So I want to point out non-linearity is all pervading, it's ubiquitous in the natural world. So in this lecture I would like to briefly explain some of the notions that has emerged during the recent times, such as solitons, integrability, bifurcations and so on, synchronization, complexity, collective behavior, etc., especially in the context of the contributions from my own group. So I would like to introduce some of these concepts, how they arose, and perhaps the historical consequences, developments behind all these notions. So to start with, I would like to point out what is the importance of nonlinearity, why nonlinearity and so on. In nature, things change. Everything change. Animals are born, they grow, they develop and they die. So do plants. Planets move around all the time, chemicals interact, crystals grow, clouds on the atmosphere or the waves on the water surface. Everything changes. Even inanimate things like this building, the chair, etc. If you wait for sufficiently long time, 10 years, 50 years, 100 years, etc., things would have changed. So everything changes. Change alone is unchanging, as Lord Krishna tells Arjuna in the war front. And the understanding that this change alone is unchanging, perhaps you can, in the modern times, from scientific point of view, you can go back to the times of Newton's and Newton's laws. Newton's laws, as all of us know as physicists, represent essentially how these changes take place. In particular, if you look at the second law, you deduce the equation of motion. The rate of change of momentum is directly proportional to the force acting on it. So the force P equal to mass into velocity. Velocity itself is dx, rate of change of displacement. So dP by dt is directly proportional to the force F, and proportionality constant without loss of generality you can put it equal to 1 dP by dt equal to F, which when mass is taken to be constant, which need not be true all the time, but most of the cases mass is constant. Then essentially you can put these changes, how they occur for a single particle system in the form of a second order vector differential equation, md square r by dt square, where the force could be function of the position, the velocity and any external influence, so which I represent as t. So which is a mathematical equivalent representation of the nature of the physical system. A mathematical equation, second order differential equation for this vector function, vector r. But you associate this mathematical entity with the actual physical system by assigning appropriate initial conditions. It's a Cauchy initial value problem. That means given the initial position and velocity, this is a second order differential equations. So you have to assign two initial quantities, the position and velocities without loss of generality, which I will call as the initial instant. You can take it as any instant. So the problem then, the physical problem of change, is this initial value problem. Given this initial condition subject to the system evolving according to this differential equation, find r of t for all future instants of time. Once you know r, you also know r dot, and so the problem can be in principle solved given the whatever form of the force that is acting. So whether it is the pendulum, simple pendulum, or the Kepler particle, the two body problem can be converted into a one body problem as you do in classical mechanics, or the spinning top, or any other single particle system. So you can essentially write it as a Cauchy initial value problem. You can extend this study to n body problem. So by writing the corresponding equation of motion given the corresponding force, which is a function of all the position variables, n position vectors and the corresponding velocities and the external influence t. For each of the variation of the position vector, you have a second order differential equation. So essentially you have a system of coupled, n coupled vector second order differential equations. And the corresponding initial value problem, Cauchy initial value problem, tells you how this n particle system, whether the n particles 10 power 23 molecules in this room, or the galaxy, the solar system, or the galaxy, or the gas molecule. So whatever the complex system you have essentially given the force and the initial positions, then the problem is to essentially find what is the future development of these n particle positions, and so the velocities and so on. So Cauchy initial value problem. And this point that once you have this differential equations as Cauchy initial value problem, in principle you can solve and you can determine the future. So which force which made the great mathematical physicist Pierre Simon de Laplace to climb towards the end of 19th century that everything is known about nature. Because essentially, once you know the force acting on all the particles in the universe, and given the initial condition, you can always determine the position. So this is called Laplace dictum. But of course, you know that Laplace was far away from the actuality. There are several limitations in this Newton's formulation. Okay. When n is very large, like 10 power 23, etc., the problem is extremely complicated. Even with supercomputers, you cannot always determine the position of and solve this n differential equations, 10 power 23 coupled differential equations. And moreover, we are not interested in the individual dynamics of each of these individual particles. What we are interested is in some macroscopic observable quantities, the statistical quantities, the average quantities. So you require an average mechanics, statistical mechanics, that is sufficient at that level. And of course, here you say given the initial positions, initial conditions, initial position and velocity, there is always limitation when you go to atomic world, subatomic world, measuring the position and velocity simultaneously at a given instant of time. There is a Heisenberg uncertainty principle coming into picture. So there is again limitation. So you have to modify. It is not that this mechanics is wrong, but you have to modify by incorporating the Heisenberg principle into account, into the description. You require quantum mechanics. Similarly, here I have not put any bound. The space is infinite. The particle can exist anywhere. But what about the velocity? There is always, in Newtonian mechanics, there is no limit on the velocity. But you know that in reality, no material particle can travel, can approach, can reach the velocity of light. Only light itself can travel with the velocity of light. You have an upper bound. So you have to incorporate that fact into the mechanics. Then you require relativistic mechanics. And in fact, you know that when you go to space and time can itself mixed, you have a general relativity and so on. So you require, for cosmological description, you require even more general relativistic mechanics and so on. So these are some of the limitations of Newtonian description. But in recent times, but 5 decades ago, it was also realized when you look at this set of differential equations, what about the form of this force? The nature of the force. So whether this force is linear or non-linear can make a lot of difference. So what is this linearity? What is this non-linearity? Why non-linearity can make a change, can make a difference? So let me, to explain this in simple terms, let me look at the very simple example every physicist know, a linear harmonic oscillator. Mx double dot plus kx equals 0. K is the force constant, or dividing by m, I write x double dot. X dot means d by dt. D square x by dt square plus omega naught square x equal to 0. Omega naught square is nothing but k by m. Okay. As a mathematical equation, this is second order differential equation. It's a second order linear differential equation. And this equation, you can immediately see that it admits two linearly independent solutions. X1 equal to a cos omega naught t. Just substitute, you will find that solution. Take the second derivative, then you find these two terms cancel. That is a possible solution. So also sin omega naught t, that is also a possible solution. But these two are linearly independent. You cannot write cos omega naught t as just proportional to sin omega naught t, but they are non-linearly related. So they are not linearly related. And you also find that you can take a linear superposition of these two solutions. A cos omega naught t plus b sin omega naught t is also a solution, the most general solution, where a and b are arbitrary constants. They could be even complex constants. So the linear superposition also leads to a possible and most general solution, and which you can write as a cos omega naught t plus delta. And as an initial value problem, you choose the initial condition suitably, and so you can get x of t as a cos omega naught t. You start with an initial position x of 0 equal to a, capital A, and x dot of 0 is 0. Then you have the general evolution as x of t is a cos omega naught t. So in this system of, in this particular linear differential equation, linear superposition principle is valid. Okay. If If you have sufficient number of linearly independent solutions, their linear combination is also a solution. Now take another simple example where I have introduced a non-linearity, a term which I call as anharmonic forcing. So lambda x cube. Okay. Then if x1 is a solution and x2 is another independent solution, under no circumstances ax1 plus bx2, where a and b are arbitrary constant, can be a solution unless a equal to 0 and b equal to 0 simultaneously. So you have, for example, x equal to acn, the elliptic function, acn omega t plus delta, where now you find omega is not just omega naught, but omega naught square plus lambda a square. The initial state, initial position also comes into picture. The frequency now depends on the initial state also. The system remembers its past. Okay. Dependence on the initial condition, the qualitative behavior of the system depends on the initial state. Okay. And then there are other quantities, the modulus square, which also depends on the initial state. But observe, when there is no force, this new force lambda equal to 0, k square is 0, in which case Cn, the elliptic function Cn becomes cos, the previous solution. But otherwise, you find in this presence of such a force, you have the frequency depending on the amplitude on the initial condition. And this dependence can sometimes become sensitive to the presence of the initial condition and highly sensitive. Particularly, for example, even in this simple case, if we add an external force f cos omega naught t and a damping, so this is called duffing oscillator, the standard problem, which can lead to the so-called chaotic behavior, sensitive dependence on initial conditions. So this kind of forces which do not admit linear superposition principle, when linear superposition principle fails, leads to what is known as non-linearity, non-linear force, non-linear dynamical systems. So non-linear differential equation, non-linear dynamical systems are systems where linear superposition principle fails. So that is the major difference between the linear system and non-linear systems. So why should one worry about such a classification? Now, linear differential equation is based on the linear superposition principle, and all the mathematics that we learn in our mathematical physics course and so on, the Laplace transform, the Fourier transform, the spectral, the various spectral methods, Green's function techniques, they are all based on the linear superposition principle. Once you go to nonlinear differential equation, the methods and techniques to solve such nonlinear differential equations are almost non-existent. Each nonlinear differential equation is a class by itself. So you have to work in a new way to understand any such nonlinear system. This leads to the development of the various developments in nonlinear dynamics. And during the past 4 decades, we have one has tried to understand the effect of such introduction of such nonlinearity, nonlinear forces, and so nonlinear dynamics. Okay. So I will very briefly introduce you the various consequences that one has encountered during the past 4 decades in the next 30 minutes or so. So in modern times, the problem of nonlinearity can be ascribed to original works of these 3 great people, Enrico Fermi, John Pasta, and Stanley Ulam, at the end of World War. So you know that the World War stopped when the nuclear bombs were dropped on the cities of Hiroshima and Nagasaki in 1947 or whatever it is. The war stopped, and the nuclear bombs were designed essentially at Los Alamos National Laboratory. So all the American scientists, physicists, etc., have confidentially worked at Los Alamos lab. And for the war effort, this MANIAC computer 1 was made available to these scientists. And at the end of the World War, this was open to universities, this MANIAC 1. And Fermi, Enrico Fermi, who was also involved in this war effort, he wanted to understand the working of a computer. So this once Maniac 1 was open for the general research. So he put the problem to John Pasta, a computer scientist, and Stanley Ulam, mathematician, essentially to understand the equipartition theorem, ergodicity property in statistical mechanics. So, and check, he asked them to check whether, equipartition theorem is, one can check from the analysis, the numerical analysis, whether it's valid and so on. But unfortunately, before the work could be completed, Enrico Fermi died of cancer. But by the time he was in sick bed, the results came up, the first results came up. But by the time the results could be completed, he died. So the other two people didn't want to publish the paper without the approval of Enrico Fermi. So the results were circulated as an internal report, as LA 1940. So under the title Studies of Nonlinear Problem. The important results of this work is that you consider the dynamics of a chain of weakly coupled nonlinear oscillators. So this is the problem which you study in classical mechanics. A similar problem, a linear limit of this problem you study in the case of transverse vibration of a bar, of a rod. So what you have is essentially a system of mass points connected by forces, the spring forces. Okay? Nearest neighbor forces. So ith particle is being interacted by I minus 1th and I plus 1th. So an one-dimensional chain of particles with mass m, all equal masses. Okay? Ith particle is connected to I plus 1th and as well as I minus 1th. So the corresponding force, small f, is the force. It could be a linear force. That is what you study in classical mechanics, the transverse vibration of a bar. So what Fermi suggested was you introduce nonlinear force into the problem, like quadratic nonlinearity or cubic nonlinearity or broken nonlinearity. So see whether the equipartition theorem is valid for that kind of problems. For certain reasons, it was suggested you consider 32 particles or 164 particles or 128 particles or powers of 2. Okay. And then Pasta and Ulam, along with the secretary Singu, they started analyzing with Maniac 1, and the result of which is this particular famous FPU plot, Fermi-Pasta-Ulam plot of FPU experiment. So what does this plot say? The x-axis corresponds to some normalized time, some omega 1 t by 2 pi. And y-axis corresponds to the corresponding, if you have 32 oscillators, 32 modes, E1, E2, En, E32 or 64 modes in some units. Okay. So you start from an initial condition where all the energy to the system is given. These are energies of linear normal modes. You know, the linear systems admit the so-called linear normal modes in classical mechanics. You know, for these linear normal modes, you give the energy, most of the energy to the first mode and almost no energy to the remaining modes. And then you allow the system to evolve and you look at how the energies gets distributed as a function of time. You find when you have a large number of systems and they are interacting, you expect in due course the modes interact and because of the interaction, the energy gets given back and forth, and if you wait for sufficiently long time, the energy gets redistributed almost equally. And that's what they've observed. The first mode loses energy, second mode gains energy, third mode gains energy, and so on. But then, to their great surprise, after a characteristic recurrence time, you see, after 160 or odd time units, the first mode gets back almost all its energy. The other modes lose almost all its energy. Now you integrate numerically for further time. Again, after the same characteristic recurrence time, the same thing repeats. Now, even now, this analysis is being carried out with supercomputers, and no violation of this recurrence phenomena has been encountered. So this is a true phenomena. So this has put in to effect lots of questions among physicists and mathematicians. So what's really happening? Is equipartition theorem wrong, or ergodicity principle is wrong, or what is happening here? So this has set in motion a lot of different approaches to understand the Fermi-Pasta-Ulam experimental results. And one approach to understand this problem, as you also do in classical mechanics in connection with the transverse vibrations of a rod, so you make a continuum approximation. So instead of nth, the displacement of the nth particle, so instead of treating as a discrete dynamical variable, you take it as a continuum variable. A is the lattice parameter. So from one end, so instead of n, you can write as yn a into t. And when n is large, you can treat that as a continuous variable. So you can treat that as y of xt. And then nearest neighbor points, you can Taylor expand as y plus a dy by dx plus a square d square y by dx square. So you substitute into the equations of motion, Newton's equation of motion, then you will find that you will have a wave equation when there is no nonlinear force present, 1 over c square d square y by dt square d square y by dx square. But that is a very limited approximation. But if you introduce a nonlinear effect, then there are changes. And if you introduce an appropriate fourth derivative term, then after appropriate transformations, you end up with this very famous partial differential equation. It's called Korteweg-Debris equation, simply KdV equation. So this is a third order nonlinear dispersive wave equation. The middle term is the nonlinear term, which destroys the linear superposition principle. But if that term is not there, you have a linear dispersive system, the standard kind of waves that it admits, wave packets it admits, and so on. But the presence of this term makes the entire differential equation of a new category, a nonlinear partial differential equation. And this equation, yes please. Yeah.
In the plot that you had 2 slides back, so the modes correspond to patterns of oscillation of the...
Yeah, the modes, so if you have a system of linear oscillators, then you can always make a linear transformation to new set of variables in which these modes are uncoupled like harmonic oscillators. So those are called linear normal modes. Normal modes, the way in which the standard oscillators oscillate. So those are called normal modes. Yeah. Yeah, in those normal mode variables, how the energies look like when you include the nonlinear term also. Yeah.
And how does this u relate to the y's?
Yeah. Yeah, u is dy by dx. So this differential equation along with this fourth derivative term. So this is called an asymptotic analysis. So you can simplify this equation by defining dy by dx equal to u or something. So that you end up with this. Yeah. So this is a nonlinear partial differential equation, the Korteweg-Debris equation, which was deduced in 1895 by 2 Dutch physicists, Korteweg and Debris, to describe a phenomena which was observed by a Scottish naval architect called John Scott Russell in 1834, August 1834. So he was observing the motion of a boat drawn by a pair of horses along the canal connecting the cities of Glasgow and Edinburgh in Scotland. He was working for the East India Company, which was, his task was to design appropriate ships so that long voyages can be made safely. So he was traveling, because in those days boats were drawn by a pair of horses along one of the sides of the canal. So he was observing this boat being drawn by a pair of horses on a horseback. For some reasons, the boat suddenly stopped, but not so the mass of water which has collected around the prow of the vessel. This water which was collected started moving forward with great velocity, and then he observed the collection of this water was in the form of a huge rounded rounded shape wave, and it traveled without change of form or diminution of speed for over 1 mile or 1.5 mile. He followed it on horseback 1 or 1.5 mile, and then after that, because of the winding of the channel, it was lost. But this man, he came back to the laboratory. He had a lab in his home. He designed similar water channel. He dropped weights at one end, and he created similar waves, and he measured the relationship between the amplitude of the wave and the velocity of the wave, and he got a relationship, empirical relationship, in 1834. And he published these results as a British Association report in the year 1844. But then the great mathematical physicists like Stokes, Airy, etc., they refused to believe what John Scott Russell had observed. They said, you had observed just half of a sine wave or a cosine wave. It has nothing to do with an isolated wave and so on. So he died as a dejected person. But in 1895, these two Dutch physicists, starting from the basic laws of fluid mechanics, they deduced the Scott-Russell phenomena, and they ended up exactly this equation. And they also showed that this equation, if you look for a wave solution, you get elliptic function wave, the limit of which you have a solitary wave, an isolated wave. One is familiar with sine wave, cosine waves. But here is a wave which is of the form secant h square, hyperbolic secant h, x minus vt. And observe also, this is the amplitude and this is the velocity. So the larger the wave, the larger is the velocity, and vice versa. The shape of the wave is like this at any instant. And since you have secant h square wave, this just translates. The wave doesn't change its shape or speed. So isolated wave, solitary wave, traveling without loss of form or diminution of speed. And exactly 65 years after Kotabek-Devery's investigation, Norman Zabisky and Martin Kruskal, in analyzing this Fermi-Pasta-Ulam results through this asymptotic analysis, obtained exactly the same equation. So this forced this Martin Kruskal, who was the inventor of the notion of solitons, and is the mathematical physicist, Princeton Plasma Physics Lab, and so he was considered to be father of the theory of solitons, and he later on, he also became a collaborator to us. He visited Trichy many times later on. So what Kruskal and Zabisky did was, they tried to analyze the Kotabek-Devery's equation numerically to start with. So this is the picture, the result they got. You start with a periodic boundary condition, that is this curve, and then you analyze how this periodic wave evolves according to the Kotabek-Devery's equation. So for some if you wait for sufficient time, you get this dot 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 pictures. So the wave gets distorted. But then if you wait for sufficiently long time, you get a series of pulses. So asymptotic evolution, you get a series of pulses just like this, isolated waves like this. And then, as I have pointed out, these waves have the structure, the larger the wave, the larger the velocity, or So as a consequence, as these waves, they are unidirectional waves, they propagate from left to right. So the larger wave will soon catch up smaller wave, and after interaction, to their great surprise, it passes over and interacts with the next wave, and so on. And since you have periodic boundary condition, it again repeats here. So the original shape after certain time recurs back. So, which explains Fermi-Pasta-Ulam to some extent, but it also leads to new possibility, new structures because of the non-linearity it leads to. And in particular, if you look at two such structures, localized structures, one solitary wave, another solitary wave traveling to the right, you find this is the x-axis, this is the amplitude, and this is the time axis. So, as time progresses, you find this is the initial state, and as time progresses, the larger one travels with higher velocity, soon catches up the smaller one, interacts. After interaction, they come out to their great surprise without change of form or diminution of form or change in velocity. It is like pure elastic collision, billiard ball like collision, except for a phase shift. So, solitary waves undergoing collision, after collision they come out without change of form or diminution of speed. So, they call such waves as solitons, like particle like structure, they call solitons. In fact, they went on to find a newer method of solving this differential equation, partial differential equation analytically, and they obtained even more general solution than the one I pointed out, which can explain exactly this phenomena. So, this is called two soliton solution, and you can proceed further, you can get n soliton solution, and that was the birth of soliton, 1967, the theory of solitons. New physics leading to new integrable systems. These systems admit infinite number of such solutions, infinite number of integrals of motion, and so on and so forth. A greatly interesting theory. A new method called inverse scattering transform method. So, you can associate this non-linear partial differential equations with two linear differential operators L and B. L is the standard Schrodinger operator, and B is a third order self-adjoint operator. L psi equal to lambda psi, psi t equal to B psi. Now, if you take the compatibility of these two relations where this unknown function u of the Korteweg-de Vries equation occurs as coefficients, then you find the compatibility of these two relations is the Korteweg-de Vries equation. So, that leads you, if you start from an appropriate initial condition, a three-way process you can develop, and that leads to the so-called inverse scattering transform technique, and such a technique leads to the notion of solitons. So, you associate a nonlinear partial differential equation with appropriate linear differential operators. So, this would have become a mathematical curiosity had it worked only for this Korteweg-de Vries equation. So, this was 1967, but in 1970s and 80s etc., many new entirely different equations have been shown to possess similar kind of solitary wave structures and soliton structures for different forms of L and B. It could be linear differential operators like this, or matrix differential operator, 2 by 2 first order differential operators, 3 by 3, n by n, and so on and so forth. So, that has led to the notion of solitons, theory of solitons, integrable systems, etc. So, one immediate application, possible applications was tsunami of 2004. Okay. You had that great earthquake of Sumatra Islands, 9.2 Richter scales, which sent in huge tsunamis all around. It hit Thailand and many other countries nearby. It came to the East India, particularly Chennai and other areas, and traveled as far as Somalia and Tanzania. So, such huge waves about to strike a city of Thailand and so on. So, these kind of waves which travels without loss of speed or diminution of height, etc., can be described ascribed to this kind of solitary structures and so on. So, that is one possible application. So, but there are many other possible applications of these solitary structures. When you have when you send intense light across optical fibers, So, nonlinear wave propagation, because of intense light, you require nonlinear wave equations under certain suitable approximations. They lead to what is known as nonlinear Schrodinger equation. And if you have multi-modes, you have coupled nonlinear Schrodinger equations. So, these systems also admit this kind of solitary waves. And in 1995 to 7, we found that such solitary waves, wave propagation in coupled optical modes, this is called Manakov equations, can lead to new kinds of solitonic structure. So, they do undergo collisions, but during collision, individual modes can undergo certain changes in their structures according to certain rules, logical rules, which could lead to the construction of optical logical gates. The total energy in each mode is preserved, but within that total energy, individual modes can exchange energy. So, it was found that, for example, to computer scientists from Princeton, they pointed out computing with solitons, optical computing. So, at this point it appeared that transactivity and elastic collisions were somehow antagonistic properties that integrable systems were doomed to be oblivious. A pleasant surprise awaited us. The surprise came in the form of paper by Radhakrishnan, my former student, Lakshmanan, and which gave a new bright two-soliton solutions for the Manakov system, and that led to non-trivial collisions, and which allows one to construct logic gates through which optical gates can be constructed. And Manakov solitons have been recently observed experimentally. So, such non-trivial solitonic collisions are also possible. Now, very recently we found that it can also lead to even more general soliton structures. So, very recently, a couple of months back, we published these results, what we call as non-degenerate solution. That leads to very many interesting new structures, both in optical fibers and what we call PT symmetric systems and so on. So, they have a lot of interesting applications. Please.
What is transactivity?
Yeah. Yeah, transactivity means when they undergo collisions, undergo interactions. So, what kind of activity can happen? So, the standard kind of solitons undergo elastic collision. I said billiard ball like elastic collision. But then the results we pointed out in the case of Manakov model can have a new kind of interacting solitons where their amplitudes can change in a particular way, and that can lead to the construction of optical gates. So, that is what so the standard ones of the integrable systems, they lead to elastic collision property just with phase change alone. But then we also pointed out there exist systems where which solitons can collide, where amplitudes can also change. State change can take place. That is what is explained here. I am not giving the expressions, but because of these state changes, logic gates can be constructed. So, all optical gates can be constructed, and that has also been observed experimentally. So, I am not going into the details, but you can get all the further details from some of these papers.
From a layman's perspective, there can be significant changes in both the waves, and yet the energy be almost conserved.
Energy will be conserved. The total energy will be conserved. Okay. So, lots of developments are still taking place in the study of this system. So, I will not go further into the details. Few more details about solitons. So, again, so this simplified version of what I have pointed out, they lead to new kinds of structures, periodic structures, breather solutions, but the limiting forms of which, so this is the periodic structure which this nonlinear Schrodinger type equations admit, but in certain limits they lead to what is known as rogue wave solutions. These rogue waves are waves which can suddenly appear and disappear in no time. So, such waves have been experimentally observed. Seafarers have observed this kind of structures. They can even destroy ships and so on. and they have a limiting form of the so-called breather forms I have written here. It's a long expression, I cannot go into the details, but the limiting form of which are these. They are localized at certain point in space and time, and so they suddenly appear and disappear without a trace and so on. So the rogue waves are certain important class of structures which explain some new features which one encounters in very many situations. Not only in Cs, but also in Bs, optics and so on. In recent time, experimentally they have been observed such rogue waves. So the point is that study of nonlinear waves can lead to very many interesting structures which correspond to such waves which occur in nature. So that is one aspect. This has also led to very many notions on integrability, because these are all very beautiful mathematical structures. They have geometric, group theoretic, singularity, what I call singularities and solution structures these soliton equations possess. As a consequence, new mathematical methods can be developed. So over a series of papers, we have developed a new method called modified Prelesinger method to identify, given a nonlinear system, whether it's integrable, under what conditions they can exist. So through several methods, symmetries, Darboux polynomial method, etc., and ultimately linearization method, we have identified many interesting dynamical systems. Low dimensional integrable system, the earlier one I have pointed out are partial differential equations, but even finite dimensional differential equations can lead to many interesting integrable systems. They lead to the notion of non-standard Lagrangian Hamiltonian. One is Matthews-Lakshmanan oscillator, which as a PhD student I had identified, but now I find that many interesting properties are associated with this. I will just point out what that system is. Similarly, a few years ago, some of my students, Chandrasekhar, Sindilwal and Lakshmanan, we identified a particular integrable systems. Now we understand this as a PT symmetric nonlinear system, which has got many interesting properties. Unfortunately, I cannot go into the details, but this is what the Matthews-Lakshmanan oscillator is. That you have x double dot plus kappa x equal to 0, the linear harmonic oscillator, to which you add this so you see all nonlinear terms, non-polynomial terms, which linear superposition principle fails, and they are associated with certain Lagrangian and Hamiltonian. They are not standard form. This is p square into x square, and then this v of x. So generalizing this velocity dependent potential which occurs. This leads to many interesting integrable systems. Corresponding quantum system is also completely solvable. You can get the energy spectrum, and three-dimensional, n-dimensional generalization is also integrable and so on. So many interesting properties have been identified. In fact, the Peter Higgs generalized this system in around 1979 and so on, and showed that this is two of the completely solvable quantum mechanical potentials of our particle moving on an n-sphere, n-dimensional sphere. So geometrical structures associated with these systems have been further expanded. Now, recently we have identified this particular class of oscillator. Again, you see x double dot plus lambda x harmonic oscillator, to which an unharmonic term has been added, and for which now we add a nonlinear position dependent velocity damping term. This equation is completely integrable in terms of very nice functions, and you find for a special class it has a Lagrangian Hamiltonian, which is not of the standard form, but of the form some function into x square plus some function of p. So x square, quadratic in x square. You can quantize this system by going not to the coordinate space, but to momentum space. So in momentum space x square you can replace by I cross minus cross h square d square by dp square. So the standard way you can quantize. So this has led to a lot of developments of PT symmetric, in the sense you change x to minus x, t to minus t, this system remains invariant. in recent times, PT symmetric nonlinear systems have been playing a very great role, particularly in optics. So such systems have drawn great interest. So these are some of the developments on integrable systems. Integrable systems have very nice structures, though I showed solitons, solitary waves, but I try to relate it to the tsunamis and so on. But tsunami, even though it's very destructive, its structure is very nice, very coherent, very ordered. But contrary to this, even simple nonlinear systems can show very complex behavior under certain cases. This is what the great mathematical physicist Henry Poincaré, in his studies in around 1900, which is published in the book Science and Method, which is now available in reprinted version. He says, it may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible. So, in the earlier case, on the solitons, the integrable systems, etc., even though the linear superposition principle is valid, is not valid, the physical properties depend on the initial condition certain way. The velocity is directly proportional to the amplitude and so on. But they are not highly sensitive to initial conditions. But there are situations where it may happen that small differences in initial conditions can produce very large differences. Small error in the former will produce a very enormous error in the latter. So, Henry Poincaré was considering the three-body problem. So, two-body problem, inverse square type force, the Kepler problem. You can convert, you can reduce to one-body problem, and you can exactly solve. You get all the three Kepler's laws. But if you introduce the effect of a third planet or a second planet, Sun, Earth, and a effect of another planet, then the problem is intractable. Even now, you cannot exactly solve this problem. But Henry Poincaré, in the connection with that problem, he said that small error in the former will produce an enormous error in the latter. Prediction becomes impossible. And this is what, in 1963, the atmospheric physicist Edward Lorenz at MIT pointed out, as small a perturbation as a butterfly fluttering its wings somewhere in the Amazons can in a few days' time grow into a tornado in Texas. Small differences, as just like a butterfly fluttering its wings somewhere in the Amazon, can lead to a tornado-like growth in a few days' time, in finite time. Small differences can lead to very large differences. So prediction becomes impossible. So a typical example is the so-called Lorentz equations, which is a very reduced version of the Navier-Stokes equations to describe the atmospheric weather. So X and Y are some transfers, temperature, conductivity, etc. So you have certain parameters. So when you change some of these parameters, this is a nonlinear system because of the presence of the term xz, xy, and so on. And that leads to motion which is extremely complicated. Even a much more simpler version is the logistic map. So which is a very simple system, xn plus 1 equal to axn. It's a map. You are mapping xn at the nth moment. Now time varies in a discrete way. n equal to 0, 1, 2, etc. So the variable at the nth instant of time is mapped to n plus 1th time by a parameter a. If the other term is not there, it's very trivial development. But because of this term, the nonlinear term, the dynamics becomes extremely complicated. This is what happens. I have plotted x versus a. For small values of a up to 1, the only allowed solution is 0. And from 1 to 3, you have a non-trivial solution. And you can find its stability, etc. You will find it stable. But then you find that suddenly at A equal to 3, instead of one value it gets two values, two possible values. It jumps between two possible values. Period doubles. Now at another value 3.53 or something like that, you get four possible values, 2 power 2 values. And then again at a small deviation you find 8 values, 16 values, 2 power n values. And then these are all happening at finite values of the external control parameter, what we call as control parameter. The parameter is in our control. So the system admits period doubling bifurcations. Ultimately you find even at a finite value you get all possible values admissible. Okay. A complete set of values are possible values. So the system enters into a complicated state, a chaotic state, where this is also happens in the case of a Duffing oscillator. So you have many such examples. So in all these cases what happens is, at this instance when you have many such possible values admissible, the system is extremely sensitive to initial conditions. Sensitive dependence on initial conditions. So what I have plotted is that the time n or t versus the variable. So you find there are two curves. One is blue curve, another is this orange curve. So what I am doing is I start with an initial condition and follow in this blue curve. That is the time development of this particular system, whether it's the Lorentz system or the Duffing oscillator or the logistic map. Then in that chaotic regime, so that you find the system evolves not periodically but aperiodically. The motion is always bounded between plus 1.5 and minus 1.5. So aperiodic motion but bounded motion. Now I follow the system again with an initial condition which deviates from the previous one in an extremely small way from the previous one, in the 5th decimal or 6th decimal. You find that is the orange curve. In the initial instances you find it follows exactly the blue one, so you can't distinguish, but then after a finite time there is a deviation, and if you follow further you find after 40 or 50 time units these two trajectories separate out, and it could be as large, the deviation could be as large as the system size itself. And if you take the average, there will be exponential deviation of these two nearby trajectories, nearby initial conditions. They are extremely close by, you cannot even notice the difference. But with such infinitesimal deviation in the initial conditions, you find as the system evolved, they can deviate to a very large size, as large as the system size itself. That's what Henry Poincaré called a small error in the former will produce an enormous error in the latter, and the consequence of which is small perturbation of a butterfly fluttering its wings somewhere in the Amazons can lead to a tornado in Texas in few days time. So the consequence of which, the prediction of weather over a small time could be possible, but over a longer period is almost impossible. So small changes can lead to very large changes. Why? Because of the non-linearity present in the system, the consequence of which. So this is what is known as chaos, and the study of such systems lead to the notion of chaotic dynamics and the field of chaos, chaotic dynamics. So this is the dissipative chaos. You can have similar kinds of chaotic behavior even in Hamiltonian system. This is what Shamik Gupta tries to study, I think, in his various phenomena. So it could. So this is for a simple system. It's a map, logistic map, or a Duffing oscillator. So you can consider many such oscillators combined. So you can have complex phenomena like a hurricane or a volcano or vortex when a plane is moving, or complex clouds and so on, or various patterns, chemical reactions, Belousov-Zhabotinsky reactions, or natural patterns, etc. So, which all arises because of the consequence of many modes interacting together, leading to collective phenomena. So, one possible such structure is synchronization. Okay. The systems following each other exactly, even when the original system is undergoing chaos. So, realized system coherent oscillations of two or more systems resulting in complete coincidence of states, even when they are highly individually they are highly sensitive to initial conditions. So, synchronization of chaotic system is a contradiction because the chaos, notion of chaos arises because of sensitive dependence on initial conditions. But it, when you have collection of such systems, chaotic systems combined, yet they can give rise to correlation and synchronization is possible. So, for example, is a neuron, a single neuron which is explained by Hodgkin-Huxley model or simplified version by Fitzhugh-Nagumo model or even simplified version by Kuromoto model. But if you have many such neurons, an array of neurons connected in very complex way, they can give rise to orderly motion, collective synchronized motion and so on. Or you can have a circuit, just an LCR oscillator, to which a nonlinear element is added. It's called a diode, Chua's diode. So, even that system can show all kinds of complexity, just like the Duffing oscillator or the logistic map, period doubling and then chaos, etc. The various ways, this is experimental verification of this bifurcation structure. This is called Murali-Lakshmanan Chua circuit. Or an STNO, spin transfer nano oscillator. You have nano structures, magnetic structures interspersed by non-magnetic structures and so on. They also exhibit similar kinds of bifurcation phenomena and so on. So, collective structures you can use for chaos computing. So, I asked the question, if you have such collective dynamical systems and they have coupling among them, for example, ith oscillator is connected to the jth oscillator, each oscillator is connected has d-dimensional, and they can even have time delay inside them, and each oscillator is connected to p neighboring oscillators. There could be very many connections, local couplings, or each oscillator could be connected to all other oscillators, global coupling, or finite number of oscillators, intermediate coupling, which I call as non-local coupling. So, all these phenomena could lead to very many new structures, incoherent structures where random distribution of dynamical variables can take place, or coherent structures, smooth profile of dynamical variables, chimera structures, which is active area of research in nonlinear dynamics. So, where a single group of randomly distributed oscillators, we have a collection of oscillators in which they separate out into two groups, one group a single group of randomly distributed oscillators, while the remaining oscillators are in a coherent state. So, these are called chimera states. You can have multi-chimera states, breathing chimera states, and clusters, and then ultimately chimera death states and so on. So, there are various notions that have come out. Perhaps I will not go into the details, but they can be statistically characterized. So, we have in recent times, we have identified new characterizing quantifiers in terms of what we call quantitative measures, in terms of what is known as strength of incoherence, and so incoherent states can be identified with the strength of incoherence as equal to 1 or 0 for coherent state, or chimera multi-chimera states in between. They can be further classified in terms of what is known as discontinuity measures, and so different systems can be identified in this way. So, with these kind of notions, one can try to understand even the collective dynamics of very large number of nonlinear dynamical systems. So, to conclude then, Nonlinear dynamics continues to be a very challenging and fascinating area of research. Many novel problems in physics and associated mathematics remain unexplored. What we have touched upon is only the tip of the iceberg. So, a few problems here and there one has tried to identify using the methods and techniques one could develop. And particularly when you come to chaotic dynamical systems, it is very difficult to make rigorous analytical progress. The progress, whatever progress has been made, is through numerical analysis and so on. So, it will be very valuable to identify which kind of systems will be integrable, which kind of systems will be non-integrable and chaotic and so on. So, what are the criteria that one can identify for such systems and so on. So, one can look for continued progress, and some basic references for these recent developments. I could cite some of these books and related works. So, at this point I have tried to point out the two important notions associated with nonlinear dynamical systems, namely integrable systems and solitons on the one side, and chaotic behavior and collective dynamical structures when these systems are non-integrable. So, within this one is able to explain very many important phenomena, but many features remain to be unexplored, and for young people there are lots of possibilities to explore these kind of problems, and I do hope some of you will take up these problems in the years to come by. Thank you very much for your attention. So, I will be happy to answer any questions or doubts to the extent I understand. Yes.
Okay, so please comment on my question. So, when chaos is usually introduced in notebooks, you are presented with certain systems, like given the logistic mapping or given the Lorentz system, now we can analyze what happens, then we see the strange phenomena of chaos. But it is very rarely encountered in the literature that it's not my field of research. The question, are there at least known some criteria by which one could at least suspect that a certain system would undergo a chaotic phenomena? So given a set of some autonomous differential equations, can one then form certain criteria? Is there some research still further going on?
So I try to point out there exists a systematic procedure to identify whether a given system is integrable or not. So first you can identify whether the system is non-integrable, and once you have non-integrable systems, then you can look whether it can admit, whether such a system can admit chaos. So first you have to identify whether the system is integrable or not. No integrable system can admit chaotic behavior. So non-integrable systems can only admit chaos, possible chaos. Non-integrable doesn't mean it's a chaotic, it will exhibit chaotic systems. Out of non-integrable systems, under certain circumstances, for certain parameters, it can exhibit chaos. Okay. So that you have to analyze essentially by numerical analysis.
So it's just then case to case and very individual. So you're just running and then hoping to stumble upon chaos.
Yeah, because till
do you hope that with some further analytical progress it would be possible in future to
in future definitely that's an open question. That's a question that people should look at and see, given a system, whether it admits chaos or not. For what parameters it will admit chaos. So that's an open problem. Analytical whether analytic techniques can be developed. So that's for the future too.
It's quite then modest, the advance in this question so far, very in the beginning.
Definitely. So that's what I said. You have touched only the tip of the iceberg. Yeah.
splitting into multiple branches of solutions, that's also common?
No, it's not multiple branches. The
Paths, multiple.
see, bifurcation means as the control parameter is smoothly varied at critical values, the qualitative behavior changes from one type to another. So the first one, I have period 1 oscillation. Then after a bifurcation occurs, the period doubles. It's still a periodic motion, but the period of oscillation doubles. Then period becomes 4, then 8, 16 and so on. But the control parameter is finite. You are not going to infinite values. And then at 2 power n, n is very large, occurs at very finite value. And at this stage, the system shows sensitive dependence on initial conditions. During periodic orbits, it doesn't show initial sensitive dependent initial conditions. So only during that chaotic behavior, it shows sensitive dependence on initial conditions.
And there is trifurcation and other.
Trifurcations and all in there are certain systems where people have identified. So this is one possible way in which dynamical behavior can change. But there are other kinds of routes of bifurcation. One calls period doubling route to bifurcation. That's typically one occurs. But there are other possible routes, quasi-periodic routes. There are many other routes, sophisticated routes that occur, through which system ultimately enters into chaotic regime. So that in the bifurcation diagram, then when you have this complex phenomena, in between there are number of gaps. So there you have periodic orbits. Then next chaos, how it occurs. So there are new kinds of bifurcations can occur. So many kinds of bifurcation routes have been identified in those regions. Yeah. Yeah, please.
Okay, so again, I think it will not be possible to give some answer at this stage to this question, but still maybe there are some hints, so I will try again. So, I mean, the question arises of the universal features of chaos. So, the question could be posed, you can have chaotic system and they will exhibit different sorts of evolutions which will be linked to their own internal dynamics discovered by the systems of equation guiding them. But one would expect that there are some universal features of chaos as such that could be modeled in some broader mathematical way, so more abstract, that it would be possible to reduce.
Yeah, the period doubling bifurcations, for example. So that could be identified with certain similarity behavior.
That would be universal.
Yeah, because period doubling roots, so you have certain universal number, it's called Feigenbaum's ratio, etc. Feigenbaum's constant that is associated, it's a universal constant that is associated. So one can deduce those constants through similarity transformations, etc. So it is possible.
So rather than some efforts, then which are aimed at building some, universal theory of chaos in that sense. That's what I was trying to tell. It's not one or two routes by which you enter into chaos. Period doubling bifurcation is one possible route. Quasi-periodic route is one possible. There are many, many other routes through which you can enter into chaotic dynamical structures. But eventually one wishes to unify all of those patterns and aspects in one.
This route through which you enter at chaos, there are many, many. So, and they are of different nature. So, I don't know how one would be able to unify all these procedures. So, it depends on the non-linearity and the parameter regime in which such structures occur. So, you may require different kinds of approaches for each of these bifurcation scenario.
If not, then let's thank Professor Lakshmanan once more for his visit and for the talk. So I predict that there will be T outside.